Hello, my name is David Pankaj. I'm a data scientist at SVM. Today, I will be presenting support vector machine, or SVMs. Support vector machine is a supervised machine learning algorithm which is used for classification and regression tasks. SVMs are also known as maximum margin classifiers. SVMs are applied to a variety of applications as bank fraud detection, recognition of handwritten digits, protein or cancer classification. Many ideas behind the SVM are developed by Vladimir Vapnik and Alexei Chervonenkis in 1963. Vladimir Vapnik is a Russian mathematician who is known for his contributions to the theory of statistical learning and the co-invention of SVM. SVM was rediscovered in 1990s after Vapnik joined the AT&T Bell Laboratories following the dissolution of the Soviet Union. SVM has the following advantages. It uses less memory for computation, it is efficient in higher dimensions, it is applicable for small datasets, and it works for non-linearly separable data. SVM also has disadvantages. First, it may overfit and not robust to outliers. Second, the training time increases with the dataset size. Then, if dataset is noisy, it may perform poor. Let's consider the following classification problem. Given the testing input data, the objective is to classify each sample either as a spam or not spam. So in the figure we can see green and red points, which are spam and not spam. Now let's see how SVM approaches to solving this problem. First, we iteratively generate random hyperplanes that divide data points into corresponding classes. Below we can see the equation for the hyperplane. Here, W is the weight, B bias, and X is the input. In this plot, A1 represents one of the hyperplanes. That may be a solution. But we can see that it performs not good as it cannot classify one of the red points. Here we can see another prediction, which is A2, which is also not good. And here we see finally another hyperplane that divides both red and the green points to correct classes. There are maybe the cases when there are more than one solution. For example, if we look at the figure, we can see that three hyperplanes A, B, C performs good as they separate correctly the data points into correct classes. And here comes the question. How we define which of the hyperplane is better than other? For finding best hyperplane, we first introduce the support vectors and the margin. Support vectors are data points that are closest to the hyperplane. And margin is the distance of the support vectors to the hyperplane. So answering the previous question, we take the hyperplane with maximum margin as a better choice. And in this figure, we can see that hyperplane B has a larger margin compared to previous A and C. There are two types of the SVM margins, hard and soft. Hard margin requires that hyperplane divides the data points into correct classes without any errors. While soft margin requires that hyperplane separates data with maximum margin, but it may leave some points incorrectly classified. Now, let's find the objective function for hard margin SVM. The decision boundary for the data points are W transpose X plus B equals 0. And we need to find which W and B we need to use. For finding this, we first introduce some constraints. From the training data, we have labeled positive and negative samples. And decision rule will look as the following. W transpose X plus B will be more than 1 for the positive samples and less than -1 for the negative classes. These two constraints may be combined into the following one, by introducing yk, which is +1 for positive samples and -1 for negative samples. And the width of the margin will be 2 divided by w. As we mentioned previously, SVM wants to maximize the margin, and it is equivalent to saying that we want to minimize w. Or for mathematical convenience, we want to minimize square of w divided by 2, which is L of w in this equation 5. The objective function of the SVM is finding suitable w and b that satisfies the equation 3 and minimize the L of w from the equation 5. Now let's find the objective function for soft margin SVM. We use a similar approach, and in this figure we can see that wt plus b equals 0 is our decision rule for any data points, and we can see that this decision boundary has some classes that are not correctly classified. For incorrectly classified samples, we can calculate the error in terms of the distance between the data point and the decision boundary for that sample. So objective function that we want to minimize has one more term, which is sum of the all errors multiplied by constant c. So for soft margin SVM, we want to find suitable w and b that satisfies the equation 6 and minimize the L of w from the equation 7. We have seen that for solving the hard to soft SVM, we need to solve the quadratic optimization problem with some constraint. And for solving that, Lagrange multipliers, invented by Joseph Louis Lagrange, is used. To solving the optimization problem with constraints, the objective function is transformed into the following form. During the training, only data points that are close to decision boundary contribute to the weight update. Let's see how SVM works for nonlinear separable data. If data is not separable, the data can be transformed to a higher dimensional space using the different kernel functions. In the figure, we can see that data is present in the 1D, and there is no line that can separate the data into correct classes. Let's try polynomial kernel and transform the data. In the second row, you can see our given data. In the third row represents the transformed data with a polynomial of the second order. Now let's plot our data in the 2D. As can be seen, data projected in 2D space can be classified using a line into correct classes. So kernels help to transform the given data into another space, which can be used for SVM classification or regression. Most popular used kernel functions are linear kernel, polynomial kernel, Gaussian kernel, or hyperbolic tangent kernel. There are also a lot of other kernels that can be used depending on the task.